Hey, it's Clay. Welcome to another video. This is going to be a circuit analysis for the Wurlitzer electric piano Model 700 amplifier. This is a tube amplifier for an old Wurlitzer electric piano. And I thought I would go through this circuit, first of all, because I have a friend who is working on one of these, and I thought it would be really beneficial for him to go through it piece by piece. And also that it would be fun for me to go through this because this is a little bit outside my typical comfort zone of guitar amps. This is getting into Wurlitzer pianos, which is kind of interesting, and so I kind of wanted to see what some of the differences are and what they're doing in this amp, and maybe give some of my opinions on how it could maybe be made to work a little bit better. So also hopefully I learn a thing or two about some of the differences between guitar and tube amps used in other types of search situations. So yeah, let's go ahead and dive in. So right off the bat, I'll note that we have four tubes. We've got the 5Y3, which is our power rectifier. We've got a 12AX7, which is our phase inverter. And then we've got two 6V6 output tubes. Those are power tubes. So interesting to note that there is really no preamp, so to speak, in this amplifier. Basically, you've got your two inputs here. One is a piano input and one is a record input. And they run directly into this 12AX7 tube, which is a paraphase phase inverter, which is kind of a very rudimentary type of phase inverter, which we'll get into more in a bit, straight to the output. So this amp is kind of presuming that you are sending it with a signal that's a little bit hotter than like would be coming off of a typical guitar. So something that already has some kind of preamplification to bring its level up to be appropriate for this kind of amp. So that's just kind of interesting right off the bat. Before we get into the main signal path, though, I want to start with the power supply. So this right here is where our 120 volts is coming in from the wall. Just a little thing of note, it talks about having 117 volts at 60 cycles. The voltage coming from the wall has slowly crept up year by year. So you can actually take a multimeter and obviously do it safely, but you can test the voltage in your wall. I think the last I tested mine, I was about 123 volts. And so if this amp was expecting to see 117 volts on the input, remember that this is going to go through the power transformer, which you want to think of as like a multiplier. So any difference, so if we've got 6 volts higher in the wall, that's going to get multiplied by our windings ratio. So our voltage could be 20, 30, 40 volts higher than what the amp was initially expecting to see. So basically that'll impact the bias of the tubes, which we'll get into later, but just be aware of that. Also, this is a 2-prong power cord, which is no longer, I think, safe or acceptable. I would use a 3rd prong that would be here that you would simply connect a wire to, and then use like a crimped bolt washer. So it's basically got a ring terminal type deal, so you can solder the wire on one end, and then the other side of it includes a ring washer that can be bolted securely to the chassis. And I would usually pick a bolt for the power transformer and just use a dedicated bolt that is only dedicated to clamping down that safety ground for our 3rd prong. Then you need to figure out which of these is hot and which is neutral. You want to send the hot signal on this path, because this has our fuse. Now, I would think I've also usually would typically see a power switch in here as well, but you just want to make sure that your hot signal is running through the fuse, because otherwise, if you send the hot signal on this path, you send it into your transformer, and then the only one on the secondary side does it complete through the transformer into the fuse. So if your fuse blows, you've already had that high voltage surge going through your transformer. So just as a safety bonus, make sure you fuse and switch the hot side of your power input. Now this, to me, looks like the infamous death capacitor, and I would recommend that you would simply remove this from the circuit. What the idea here is that if you do have high voltage here, the capacitor could help kind of filter some of that to ground. But the issue is that if this capacitor fails and becomes open, you could this would basically just be like a straight up wire connection to ground, and you could be sending your 120 volts of alternating current to ground, and ground is also usually connected to other things like your guitar strings. Now I realize this is a piano amp and I don't think the piano keys are conductive, but any other metal bits would be conductive. So I would just simply remove this capacitor from the circuit entirely, and I would again prefer to just have a fuse and a switch on this hot input. So this voltage, it looks like it goes into this weird cable socket, which I'm not even fully sure what this thing is doing, but then I'm guessing it goes from pin 3 to pin 2 and then right in here. So this is the primary side of our power transformer. So the power comes into these two coils. It goes through some kind of induction, which is still a little bit of a mystery to me, but then because of the windings ratio in the transformer, the voltage is then multiplied and you have multiple secondary taps. So this is your primary side, this is your secondary side. And if you notice on the secondary side, we've got 3 main outputs. First, right here is our 6.3 volts that is going to power the filament windings of our tubes. That would be the 12AX7 and the two 6V6s. So the filaments are what kind of creates the glowing effect that generates the electrons kind of down at the base by the cathode. And that electron flow is attracted up towards the high DC voltage on the plate. And that flow of current is what is amplifying your signal. Now, one thing I'm not certain about is whether or not there would be a center tap right here that would be grounded. And if they don't have that, which it does not appear that they do, one thing that you could also choose to do would be to do a elevated center tap, which means that you basically, and you can see here, actually it's interesting, they've got 6v6, 6v6, 12AX7, 27, 27, 4, 5, and 9. Those are your pins. But you could actually basically tap off of these leads. So you would pick one from each side, and you would want to run it into a 100 ohm resistor, and on this side also a 100 ohm resistor. Tie those ends together and then ground that. That would create an elevated center tap, which would help to reduce some noise from the filament supply. Because again, I don't believe that you have a wire that's coming out of the center tap here to help with that. So that's just one little thought that you could add to keep the noise down. Next, you have your high voltage B+, which is coming out of here, and you do have a nice center tap there. That's good. And that's going into your rectifier, the anodes of your 5Y3 rectifier. So this is your high voltage AC line. And then here on the cathode side, this is where your 5-volt filament winding comes into play to heat the heater requirements on your rectifier tube are a little different than your other tubes. So you use a 5-volt winding there instead of 6.3. And then out of this pin here, which is usually pin 8, this is our high voltage B+ DC line. So the rectifier tube converts it from AC to DC, and then this is our high voltage, which really is the main heart of the power supply of the whole amp. Okay, so next, we've got 2 main lines here. First, this one looks to me like it goes right here to like a center tap on the primary side of the output transformer, and I'm not 100% sure what's happening with that connection. So I've seen some of those before as like ultralinear taps. So maybe this is an ultralinear output transformer, but I'm not even 100% sure. And if you guys have any thoughts or comments, certainly leave them down below and let me know if you know what's going on with this tap. But that's a little different than what I've seen in some of the guitar amps that I've looked at. But then other of note is this is our B+ smoothing step-down circuit. And you basically have your large filter capacitors. We've got a 40, a 15, and a 10. And then you've got your step-down resistors, 680, 680. Now, kind of intriguing here by some of these values, I would say that it's a little bit interesting that you've got a 40 volt, 40 microfarad filter cap here in the first stage, and then 15 and 10. I'm not really sure why, they would decrease in value. The lower the value of the capacitor, the less filtering that you have. So 40 actually does a better job, but I don't know why they wouldn't also just do 40 and 40 here as well. Also, 40 microfarad at the first stage is maybe on the very high end of what you would want to see for your tube rectifier. So if you have a tube rectifier, you have a limit as far as how high you can put this first filter capacitor, otherwise it'll basically ruin the tube. And so 40, I think number 8 would be as low as you would see, maybe 15, 16 I've seen, and then maybe 20 or 22 I think would be more kind of moderate, and then 30 or 40 would be a little more on the high end. I don't think it's a problem, but I guess in my mind, I think we would want to maybe increase these a little bit. This 10 and the 15, let's just bump that up for a little bit more filtering so that it's a little bit quieter. But maybe just a personal opinion that I would have. Also, these 680 ohm step-down resistors seem a little low to me. They do create a filter, so you have an RC filter. And actually, so this is a CRC. So yeah, I'm not 100% confident right now on the math, but basically you want your filter. You can go to a website that would do a CR or an RC filter. Okay, so I decided to crunch the math, and just to give you some sources, if you go to the Valve Wizards page, it talks about smoothing and filtering the power supply. It gives you this formula right here. And the idea here is that you want to filter out DC. And so what you do is you create a low-pass filter, meaning everything above the low-pass filter is being filtered out. And if you create a low-pass filter right here as close to 0 hertz as possible, that is all of the DC. So if you put the values that you see in your schematic, 680 ohms, and I'll just use this 15 microfarad, if you plug it in to this formula, I crunch the numbers and I get 15 hertz. I also did a calculator right here, and it also gives me that 15 hertz. So, like I said, you want to be at about 1 or below that. So to me, this is a little bit odd. Whereas if we do 4.7 kilo ohms, then we're down to about 2, so we're closer. And even if you bump this up to 40, so there we go. Now we're below 1 hertz. So that's kind of where I'm getting at as far as, now if you do increase the values of these resistors, you are going to, that's going to definitely impact your voltage. So there will be some trade-off there that maybe you don't want to do. But I guess at a minimum, I would maybe increase the value of these capacitors. So even if we keep this at 680 ohms, at 40 microfarads, we're at 5. So we've reduced that a fair bit. So a little bit of kind of an odd power supply design. You could also maybe look into using a choke. That would help with keeping your supply voltage up. But anyways, just some design thoughts there. Bump these capacitors up, I think would be a good idea, at least for my own personal preferences. Okay, so upon looking at this a little bit further, maybe it gets away with it because, again, so if we have a tap off here at this point that's running into the center, and it looks like this is what's feeding our output transformer. So yeah, okay, I think I was looking at this output transformer incorrectly. So there's actually does not appear to be any filtering on the voltage that's going into the power tubes, which I think is maybe a little bit suboptimal. And then we've got these two-ish stages that are filtering into your 12AX7, which is just maybe a little bit odd. So yeah, you could maybe do some tweaks to the power supply if you would want, but if you just want to keep it as is, I understand, and just kind of bump up these capacitor values as you are able, I think would be a good idea. Like I said, anything from 8 to 40 UF are acceptable valuables, and bumping this up to maybe 30 or 40 I think would be a good choice. So that covers our power supply. Now let's get into the signal path. Like I said before, we've got two inputs. This is our piano input, and this is our record input. Now, this is a little bit peculiar to me. I'm going to start with the record input. And one thing that is odd is we see a very large 1.5 mega ohm resistor in series with this signal. And I would say this is a very large value resistor. Typically on a guitar amp, you'd see something more in like the 33K range. And I'm guessing that this is going to kind of attenuate that signal from a record player that probably already has a preamp in it. So it's kind of clamping on that a little bit. It also appears there's a capacitor here, this guy, which at 100 picofarad is going to be like it's going to boost treble frequencies that they're going to be allowed to pass over the resistor, whereas the rest of the body of the, so we're talking about 100 hertz is a pretty, 100 picofarad is going to let just the very highs go through, whereas the rest of the body of the audio signal is going to run into this 1.5 mega ohm resistor. You could maybe look at it as like a grid stopping resistor, because this is going directly into the grid of this 12AX7, but again, it's just a very high value resistor. And again, I'm guessing this has to do with impedance matching and signal level matching from what you would expect to get from a record player that already maybe has some preamplification. And then over here we've got our piano input. Now this is odd because first of all we've got this path up here into a 22 meg resistor, and then we've also got this path this way which has 0.001 cap, 470K resistor times 2. Now this looks to me like a CR filter. We just talked about our C filters as low pass, and so a CR filter would be the opposite, a high pass. So this would be filtering low frequencies to ground. I'm not sure why there are two of them that are just duplicated. To me that seems a little bit odd. But I do think this would filter out some of your very low frequencies. Some of this maybe could be like if this was a grid stopping resistor, some of this might also serve as a grid leak, helping to kind of maintain stability and bias on the grid. But yeah, this input scheme is kind of perplexing to me. And if any of you guys have any inputs, please let me know. But my typical thought for a guitar amp is you would see a resistor right on the input, about 1 meg, to help set the input impedance. And then you would see a lower value resistor like 33K or maybe two 68Ks in parallel that would be grid stopping. And I've even seen some amps that do away with grid stopping entirely. I think that maybe the concern, you maybe want a little bit of grid stopping to prevent like high frequency radio or like radio frequency oscillations at frequencies that are maybe like 30K, so beyond human hearing. But yeah, this input scheme is a little confusing to me. But we come into the grid of this tube, and then let's talk about the cathode. So that's this guy right here, goes to this resistor and this capacitor, and it looks like it is a common cathode, meaning both of these 12X7, so here's your top triode and here's your bottom triode, they both share a common cathode, meaning they're both connected to this point. So this 1.5K resistor is actually doing double duty. So it's more like an 820 ohm resistor per triode. And then the 25 microfarad bypass capacitor I think is fairly standard. So one thing you could do, like I said, 820 per side is a little bit warm of a bias. So you could basically double this resistor from 1.5K to 3K. So that each of the individual triodes would see 1.5K, and that I think would maybe center bias it a little bit better, but probably not a huge thing, but maybe just a little tidbit of that I would recommend for more optimal amplification at this stage. But like I said, this is operating as a paraphase phase inverter. So what that means is comes into our grid, and then the signal exits here at the plate. And what that means is, so you've got your audio signal here coming in like this. Then when it runs through the tube, it is amplified, so it is larger, but it also flips the phase. So it's amplified, meaning these peaks are further away from the center line, but it's also, the phase has been flipped. You see how this first one goes up and this second one goes down. So every time you run through a triode gain stage like this, you flip the phase by 180 degrees. So then the signal comes through here. This is your decoupling capacitor to block the DC voltage coming in this way. And then you run through, so part of the signal goes this way, but then another part comes through this 470K, then there's a 6.8K to ground, so these two form a voltage divider, so that's like a volume control, that it's cutting some of the volume, turning it down, and that's going to run it over here into the grid of this tube. So we go into the grid, we come out here, and the phase has been flipped again. So if right here, if we started up, down, up, now we are down, up, down, we're amplified. We run here, the signal actually loses volume because you have this voltage divider, goes in here and comes out here and is now going up, down, up. But the volume that you lost here at the voltage divider gets made up for here with the amplification of the tube. So you actually need this voltage divider, otherwise this signal would just be louder. And then you go into your tubes, and you need them to be out of phase with one another, because if you think about how a speaker works, right, it's pulsing in and out, in and out. Well, one half of the push-pull is pulling down, pushing up. And then the other half is pushing up, pulling down. So these two tubes and the out-of-phase signal is responsible for keeping the speaker to be going, operating like it should, in and out, in and out, in and out. So that's our signal path through our phase inverter. One other thing of note that I want to talk about is, so we've got these plate resistors, 470K. That is a very, very high value plate resistor. It would be more common to see something in the range of 100K, maybe even up to 220K. But that is going to help to set the load line, which would kind of affects the bias and the performance of the tube. And my personal opinion, again, would be to change these from 470K to 100K. And that's going to help your 12AX7 run a little bit more neutral, a little bit more standard. I guess the bias is going to be better, the voltage swing is going to be a little bit better, and it's just going to help the tube run more healthily, in my opinion. But then, now let's get back. So, I'm a little bit confused now about this connection. On one hand, you have right here, this is our power supply, providing our smoothed and rectified DC voltage. Coming up here, got another 18K resistor, that's fine. And then here, so we're feeding the voltage through this 470K into the plate of this tube. But then I guess what I'm not understanding is why we've basically got another filter cap here and then 22 meg to the input. Now, 22 meg is an absolutely huge value resistor, probably the largest value resistor I've ever seen. And it's so large that I don't think any of the piano input would be going this way, because it's basically going to go this way because it's an easier path. There's so much less resistance. But 22 meg, I guess what I'm not certain about is coming off the plate of this tube, I said it goes this way, but does some of that AC audio signal from your piano that's now been amplified sneak through the 470K, and then this is like a negative feedback loop that's heavily attenuated by the 22 meg? That's maybe my guess or my thought. But then I also don't understand, what is this 8 microfarad cap here doing? We're on the B plus line, so is this like a filter cap? But there's no tube here. There's no plate voltage to even smooth. Or does it? I don't know. I don't know what this is. Is this a CR filter? No, it's not a CR filter. Your guess is as good as mine. Like I said, I'm guessing that this is some kind of odd negative feedback loop. So the signal's coming out of the plate. Some of it does continue on, but some of it is fed back. Just a very small portion of it, because you got a huge value resistor here. But I don't understand why you would have an 8 microfarad cap here to ground. This is a bit perplexing to me. I mean, if it were negative feedback, I would just assume that you would take from right here and run it into this point. You'd have your 22 meg resistor. But I am not sure what these two components are actually doing. This is a bit of a mystery to me. So if you guys know, please leave your comment down below. So out of the phase inverter, we go into our two 6v6s. Somewhat straightforward. Here we've got the enter here on the grid, enter here on this grid, amplified here out on the plate into the output transformer. Same thing, plate, output transformer. Now, maybe one thing of note that's kind of interesting is we've got this 22K, this 0.001 resistor capacitor. Now, I've seen this before just briefly, and I believe that it functions to kind of stabilize the output a little bit more. But it is a bit of an odd portion of this circuit. It's a little bit beyond my understanding. But then the other maybe portion of note is over here on the cathode. So they have a shared cathode, which goes to this 125 ohm resistor and 25 microfarad capacitor. And what's odd to me is the 125 ohm resistor seems like a very, very small value. I'm more accustomed to seeing values in like the 3, 4, 5, 600 ohm range. And this is going to help set the bias of this power tube. And basically, if your resistor is so low, your plate dissipation on these power tubes is going to be really, really hot. And again, you combine that with your wall voltage. We talked about 117 being very low, and so your voltage on the 66 is going to be higher. And so I would have concern that 125 ohms on the cathode here is very low. And I would personally look to experiment with like a 390 or a 470 ohm 5 watt resistor. And I would crunch some numbers. If you go to Rob Robinette's, he's got a tube calculator here on his amp stuff page. Here we go. Tube bias calculator. This is what I use. I would enter the values that you're getting in here and try to see what kind of numbers that you get, just because this 125 seems extremely low to me. And then, you go to your output transformer into your speaker. So that's a look at the amp. I personally would maybe make a little subtle tweaks. I would for sure do the 125 to a higher value. I would probably move this up to 3K, probably bump up these filter caps. I don't know what this part is doing, but I think if you start with those modifications, cleaning up it's a vintage amp, so cleaning up the new filter caps would be really nice. It's overall a pretty cool circuit. I think you get a really nice looking amplifier out of this. So, hope you guys enjoyed this video. Let me know your thoughts down below, and I'll talk to you guys again soon. Thanks, bye.